problem up here on the board. We want to prove that f of x equals x cubed plus x minus 1 has a root in the interval from 0 to 1. A root is sometimes also called a zero. That's just going to be an x value so that when we plug it in, the function value is 0. So we're basically looking for a solution to this equation, that x cubed plus x minus 1 is going to equal 0. Now, ordinarily, if I'm trying to solve a polynomial equation, I would try to factor, and it wouldn't work so well. Now, I might try the rational zero theorem, but 1 and -1 are the only possible rational zeros that I could get here, and neither one of them is going to work. Okay. It does turn out there is a cubic formula, kind of like there's a quadratic formula. So I could Google and find the cubic formula and plug in and get the exact value of all of the roots for this function. But very often when I've got something where my usual factoring techniques aren't going to help me solve things, I might just use the intermediate value theorem instead. Essentially, this is our value of n. We're trying to show that we hit that y value, okay? And I'm going to just draw the picture here. We're trying to show that we hit that somewhere in between 0 and 1. So working on this interval along the x-axis here. Okay. So I'm thinking we're probably going to use the intermediate value theorem. So let's look at our function. It's continuous. And we're given a finite closed interval. So I don't really have to do much. I just have to point out that I noticed that I know that that is true. So I'm just going to say f of x is continuous on 0, 1, that finite closed interval. If I didn't have a continuous function on a finite closed interval, the intermediate value theorem wouldn't apply. Then remember, the other thing that we need is to have a here, a there, and an in-between. Okay. So since we were given this interval, I was given these endpoints, I'm thinking that's probably what I want to use. So let's just see. F of 0 would be 0 plus 0 minus 1. That's going to be -1. So there's my point 0, -1. I can sort of say, hey, that's down here. That's negative. That's less than 0. Let's see where we are at 1. F of 1 would be 1 plus 1 minus 1. That's 1. Well, that's bigger than 0. There's my point 1, 1. I'm just going to say, hey, that's up there. And where is 0, this number that I'm trying to hit? It is very conveniently in between. Now, it is not necessary to draw the picture as part of doing this problem. What's necessary is the write-up that I'm doing over here. Okay. But I find the picture helpful so that I'm not just memorizing words and spitting them out and regurgitating. I'm really thinking through this process. Saying, hey, if I've got a continuous function and I want to get from here to there, I'm going to have to hit what's in between. Okay. So I'm going to just put these two pieces together to really make it clear that 0 is in between those two function values. So these are the hypotheses of the intermediate value theorem. So now I can say, by the intermediate value theorem, now I'm just going to abbreviate that as IVT. That does not mean the Irvine Valley theorem any more than IVC is the intermediate value college. In this context, this is the intermediate value theorem. Okay. And what this says is there is an x value c somewhere in this interval from 0 to 1. Here it had to be closed, here it could be closed or open, such that f of c is equal to 0. Essentially, I'm just saying, hey, if I'm connecting the dots, I'm going to have to cross that line, and I'm just going to call the x value where I do that c. What I just put in that box, that's what it would be necessary to do to show your work. You've got a continuous function on a closed interval, establish an inequality to show that you've got a here, a there, and an in between, and then state your conclusion. And for some reason, a lot of times students struggle with stating this theorem. Sometimes people forget to tell me that C has to be in this interval. Well, I was asked to prove that there's a root in that interval. So if I simply prove that there's a root somewhere, that's not what I was asked to do. Okay? So do make sure that you say it's got to be in that interval. Sometimes I've actually seen students who leave that out. And I think this is because they're trying to just memorize the words they're supposed to say rather than thinking through what's happening. What we're saying is, hey, there's going to be a point where I hit n, a y value of n, where I hit a y value of 0. That's what this is saying right here. If you stop before you say that, and you just say, by the intermediate value theorem, there's an x value c in the interval from 0 to 1, I don't think we need a theorem to tell us that there are numbers between 0 and 1. You've been working with fractions for a while. Okay? So, there may be ways that you can paraphrase this information. I don't care that you're using exactly the same verbiage that I'm using, but I do care that you have these pieces. So play around with it, find a way of phrasing things that feels comfortable to you, that you're not just memorizing, so that you're able to actually say, hey, yeah, there's an x value in the right place that does the right thing, that actually hits the y value I'm trying to prove that we hit. Okay. Now, you might say, what good is this? Because we didn't actually find it. Okay. Well, that's true. And we just used the intermediate value theorem once here. But notice, right now, I know that at 0, my function was negative, and at 1, my function is positive. And that tells me that there's a root somewhere in between 0 and 1. If I wanted to get a decimal approximation of that, I could use the intermediate value theorem again. If I take a look at 1/2, if I plug in 1/2, I'm going to get 1/8 plus a half, so that's 5/8 minus 1. That's still going to be negative. Now what I just did is I cut the interval in which I know there's a root in half. I now know there's a root between 1/2 and 1. Okay. If I want to get a better estimate than that, I could choose the halfway point here. I could plug in 3/4 and see is the function positive or negative. And each time I use the intermediate value theorem, I can cut the length of the interval in which I know there's a root in half. Now, that gets a little bit tedious to do by hand, because although it's not the end of the world, I'm not crazy about taking fractions and having to cube them and then get a common denominator. But with the aid of technology, using Excel or using a programmable calculator, you could use the intermediate value theorem 100 times very quickly, and you could get that you know there's a root in a very short interval. So you can get a decent decimal approximation by repeated applications of the intermediate value theorem. Now, because I'm not allowing calculators and computers, well, except for you have to be on Zoom when you're taking your exams, but because I'm not allowing calculators and computer stuff on exams, I would just ask you to do the work that we did here, to use it once. But I want you to be aware that this isn't just an exercise that's pointless that you have to do in a math class and nobody ever uses this. This actually is useful and can be used to generate decimal approximations of things without doing anything too involved.